We're in track 7, Mass Effect, and our next speaker is Zach Cutlip from SQL Injection and Mips Overflows. And I just want to remind everybody that we do have a microphone over here on the side so that when it comes question and answer, if he can't hear you, you can use the mic. Zach?
All right. Thanks a lot for coming to hear my talk, everybody. There's a lot of people out there. Hope this talk doesn't suck. All right. Okay, so like you said, my name is Zachary Cutlip, and I'm going to be talking to you today about routing and hacking Soho routers. Now, all right, before I actually get into the meat of the talk, I just want to give a couple of shout outs. First of all is my company, Tactical Network Solutions. TNS, they let me hack on stuff, and they also pay me money. I don't think they figured out that I would probably do it for free, so anyway, it's a pretty sweet gig. Also, my friend and colleague, Craig Hefner. When you sit next to Craig every day, it's a little bit like cheating because problems that should be hard just kind of become easy when Craig is around, so I really appreciate Craig's help in all of this. Okay. What am I going to be talking to you about today? So first I'm going to go into some novel uses of SQL injection that you may or may not have thought about. I'm also going to be talking about the actual mechanics of how buffer overflows work on the Mips CPU architecture. There's just not a lot of information about Mips and buffer overflows, at least that I came across, so I did quite a bit of learning about that in this project. Also, I'm going to be dropping some O-days on Netgear routers because O-days make every talk more fun, so I'm going to be sharing some of those with you. And I'm going to be sharing some embedded device investigation techniques that are useful to me, and I think will be useful to you if you're investigating Soho routers and other types of kind of similar embedded devices. I'll be concluding with a live demo. I know whenever I go to a talk and it doesn't somehow end in a root prompt, it's almost like the talk didn't even happen. So hopefully I'm not going to disappoint you in that way. And then after all that, hopefully we'll have some time for some questions. I'll be happy to take any questions if we have time. Before I get into the technical material, I just want to say I had to be pretty brutal with what I could include in the presentation just due to time constraints. So there's a lot of material in the white paper which you should have on your conference CD, and if you find this talk to be interesting, I encourage you to read the paper. I actually walk you through soup to nuts how I discovered and developed these exploits, so hopefully you'll find that interesting. All right, so why do we attack Soho routers to begin with? What's the motivation there? Well, a successful compromise of a wireless Soho router actually yields a pretty privileged vantage point to the attacker on a user's network. So for example, attacking and compromising one of these routers exposes potentially multiple connected users to subsequent attack. Also, it exposes all of those users' internet-based communications to interception and manipulation. In addition to that, it's certainly not unheard of for people to bring these devices into work for a variety of reasons, sometimes legitimate, sometimes not so much. So a successful compromise of a Soho router on a corporate network can sometimes serve as kind of a side door into an otherwise well-defended network. Now, the specific device I'm going to be talking about today is this Netgear Wndr 3700. Now, besides being just a wireless router, it also has some enhanced capabilities, like it'll serve up multimedia to your PlayStation or your network-connected television. Also, it has a little Samba server built in, and if you plug a USB drive into it with some files, it'll serve up those files over the network to your other computers on the network. When you go on Amazon or Newegg and kind of sort by the number of reviews of devices, you actually see this falling into easily in the top 5. So it's a really pretty popular device, in large part, I think, due to these enhanced capabilities. Now, here's one particular review on Amazon that suggests that there's potentially a lot of fun to be had with this device. That bodes well, I think. Anyway, so besides the 3700, I also downloaded and unpacked and did some binary analysis in IDA on the most recent two firmwares, on the 3800, 4000, and 4400. And at least my initial investigation suggests that those devices also are vulnerable to the same exploits that I'm going to be talking to you about today. All right, so when you get a new toy, one of the first steps in your analysis can be to take it apart and actually see what good stuff you find on the inside. In this case, we find this UART header, and the UART header is really useful to connect up a UART to USB adapter, and that actually lets you connect to the device via a terminal application like Minicom and get yourself a root prompt on the device. Now, that's really useful for debugging and developing some more complicated exploits like one of the ones that I'll show you later, because it lets you get a debugger on there and actually connect to it with a debugger. Also on the back, we have a USB port, right, because it's a network-attached storage server. It's useful to us, this USB port, because the application I'm going to be talking about creates its SQLite database on the USB drive if that drive is plugged in. And that makes it easy to then get the database off the device and onto your workstation for analysis. Also, for some more complicated exploits, like I said, you'll need a debugger. So you can put the debugger on the USB drive and plug it in rather than trying to get the debugger onto the device some other way, which can be sometimes a little complicated. So one of the first steps to analyzing the software on the device is just to go to the vendor's website or FTP site and download the firmware update file. Now, I'm not going to go into the technical details of unpacking firmware. Craig's blog actually covers this in great detail. There's a lot of information about firmware unpacking and analysis on Craig's blog. So if you're interested in that, I suggest you check out Craig's blog. And in fact, there's a picture of Craig. I think he actually maintains the blog using a soldering iron. I don't really know how he does that. He's pretty crazy. Anyway, once we get the firmware, it's a pretty easy matter to just extract out the operating system kernel. And one of the things that we see is that we're running Linux on this device. Now, that's really advantageous for a couple of reasons. One is, from an analysis perspective, it opens up a whole wealth of tools and techniques to you. If you're familiar with Linux and you're already working with Linux, everything that you kind of know and your tool chain and your processes are pretty portable to this device because it's running Linux. And it's just a matter of compiling tools that can work on the device, like debuggers and things like that. Also, once you've successfully compromised the device, now you have a whole set of attack tools that are potential candidates to put on the device, and it's just a matter of cross-compiling them and loading on there. The next step is we can unpack and extract the squashfs file system that's in the firmware. And once we do that, we find this interesting application, minidlna. Now, why is it called minidlna.exe, even though we're on a Linux system? The truth is, I don't know. I don't know if that's even knowable, but at any rate, we're dealing with this application, minidlna, that actually provides the device's multimedia capability. So what is DLNA? Well, it stands for Digital Living Network Alliance, and it basically refers to a set of specifications that allow devices to share multimedia files with each other. So your DLNA connected television or PlayStation can locate video and music files on your network and then play them back for you. But more importantly to us, what DLNA represents is attack surface, right? Any kind of extra features on this device above and beyond their core routing and Wi-Fi capability are additional opportunities to find yourself some easy O-days, write up a paper, and maybe even submit it to a security conference, right? So the DLNA application is an interesting target for our research. Now, going on the internet and just kind of seeing what the internet knows about minidlna, we quickly discover that minidlna is actually an open source project hosted on SourceForge. Now, I spend quite a bit of time in IDA Pro, but I have to confess my reversing skills aren't quite to the point where I don't want to see source code. So this was actually a pretty lucky find for me. And our exercise now, our analysis essentially becomes an exercise in source code analysis. So it's pretty easy just to run strings across your binary and see what version string is in there, and then check out the right version of the application from SourceForge and just start combing through the source and looking for some low-hanging fruit. And when I was doing this, I was initially looking for buffer overflows. And I hadn't really considered the SQL injection angle, because we normally think of SQL injection as a means of accessing sensitive or valuable data, right? But what if the data in the database that you've got a SQL injection for isn't sensitive or valuable? Well, I would submit that it's still potentially an opportunity to violate some developer assumptions. And you know what happens when you assume, right? You end up looking like an ass. So I think the opportunity for SQL injection here could be kind of interesting. Now, we can just kind of grep through the source code and look for some suspect SQL queries, and there are a bunch of candidates, and one in particular pops out because, like I said in the beginning, I was actually looking for a buffer overflow, and it's this unbounded sprintf. Now, I have to say, this isn't actually an opportunity to get execution on the system. Unfortunately, the most you can do here by overflowing this buffer is crash the application. But no worries, we still have a candidate for SQL injection. What's happening in this function is when the DLNA client wants to browse album art, it sends an HTTP GET to the application. And then the application pulls out the numeric ID in the URL and passes that numeric ID into a SQL query. And then it pulls out whatever path is in the database that points to the album art and then serves that back up in response to the HTTP GET. Here's a closer look at what's going on here at this printf and then in the subsequent SQL query. Now, we can simulate what's happening just by taking that URL and putting it into our web browser and requesting album art ID number 1. Now, the URL is actually being tokenized on the dash, so everything the dash and after is just ignored. So as you can see, you can put whatever string after the dash you want. But at any rate, the album art is served up. Now, to test to see if we have a working SQL injection is actually pretty easy. We just go to wget, and we give wget the same URL that we put in the web browser, except after the numeric album art ID, we terminate the SQL query with a semicolon, and then put in our injected SQL query. And here's the SQL query that will attempt to create a bogus record in the database. Now, like I said, you can just pull the database in off of your USB drive and then analyze it. And when you do, sure enough, you see a record got created with ID 31337. So we have a working SQL injection, but there's some good news and bad news with this vulnerability. So first of all, it's trivial to exploit, and we have full control over the database, and we can execute virtually any SQL query we want with this injection. The bad news is there's no valuable information really in the database, right? Because it's just metadata about songs and videos. In fact, if the database is completely blown away, it immediately gets recreated. So this attack doesn't really yield you a lot of access. However, if we go back to the vulnerable function that I showed you earlier, what is happening is it's getting the result from that SQL query, which contains a path to an album art file. The results from the SQL query are not sanitized at all. So whatever that path points to gets served up in response to the HTTP GET. If we look at a legitimate entry in the database for an album art file, we see it literally is an absolute path to a file in the file system. So maybe we can just create use our SQL injection to create a record that points to something else. Again, going back to wget, maybe we can create a record that points to Etsy password. And then with a subsequent wget, pull back that fake album art file that we've created a record for, and we see the contents of it are Etsy password. More to the point, your admin password in clear text. Okay, so you might even say we have a bonus vulnerability here that they're storing passwords in clear text on the file system. So at this point, in 2 wget commands, I've gotten the admin password to your router. So I could log on to the admin interface and, let's say, change DNS settings, mess around with routing tables, maybe even upload a Trojan firmware to your device and take full control over it that way. But we haven't yet gotten code execution on the device. And like I promised at the beginning, I want to give you a root shell. So I'm not going to stop until we have a root shell on the device. Now, if, like me, you read Aleph1's seminal stack smashing paper, and then were disappointed to find that it doesn't really work that way in the real world for a variety of reasons, chiefly among them it isn't 1996 anymore, I can reassure you that you need to look no farther than Soho routers, okay? And we can just kind of grep through the source code for some risky string handling functions like strcat, sprintf, and strcopy, and we see a ton of potential opportunities for buffer overflows. Now, if you missed that, let me give you a closer look. That's 265 potential opportunities for execution in this one application. This is completely ridiculous. One in particular stood out and caught my eye in this really gnarly function that I've abbreviated way down so we can fit it on the screen. And this function is called callback. And callback is handling the results of SQL queries. And let me give you a closer look at this unbounded printf here. So what we're doing is actually creating a URL string with several fields from the result of a SQL query. And one field in particular is called album art. Now, let's look at the SQL query whose results we're processing. It's this kind of big left join, and I'll give you a closer look, and there are a couple of details I want to call out to you. One is album art is a field on the details table, and this query is a left join on the details and objects table, and that's going to be kind of important in a bit, and I'll get to that in a minute. But when we look at the schema for the details table, we see that album art is an integer in that table. And there are two things to note about that. One is, due to a feature in SQLite called type affinity, if SQLite can store the value in album art as an integer, it will. If it can't, it'll just store the raw bytes, which is awesome because that'll let us potentially store a string in the album art field. Also, callback, the vulnerable function, is attempting to validate the results of the SQL query using the A2I function. Now, if you know how A2I works, you know that all you need to do is pass it a string that starts with a number, and then everything after the number is ignored, right? So this is actually no validation at all and is pretty easy to bypass. Do we have an exploitable buffer overflow? We have a buffer overflow, but is it exploitable? Well, we have full control over the database, and if we're going to exploit it, somehow we need to stage some shellcode in the database and then subsequently trigger a query of the state of the shellcode back out of the database so it gets executed. We are dealing with a limitation regarding our SQL injection. Like I said, it can crash the program, but this particular SQL injection couldn't actually get you execution by itself. We need to limit each SQL injection to about 128 bytes by the time you take into account overhead, like with the SQL syntax and things like that. We're trying to overflow a buffer that's 512 bytes big. So how do you do that? Fortunately, SQLite comes to the rescue with the concatenation operator. So just in multiple passes, you can build up your string in the database as long as you need it to be. So how do you trigger a query of the staged exploit? Well, when I was initially developing the exploit, I was actually modeling an entire DLNA client in Python using this library called Coherency. And that was a little flaky because due to the way SSDP and UPnP work, sometimes it would trigger the exploit immediately, sometimes it would take a little while. It was pretty annoying. What I ended up doing is just capturing the conversation in Wireshark, like so, and then popping out the necessary SOAP request that will trigger the exploit. And you can just play back that SOAP request using wget and just bail on the Coherency library altogether. Now, you're going to need a couple things to develop this exploit. So first, you're going to need console access to the device via the UART connector that I showed you earlier. Also, you're going to need GDB server cross-compiled for Mips, and you're going to need GDB on your workstation compiled for the Mips target architecture. In order to test the vulnerability, just attach GDB server to the target process on the device and connect your local GDB over the network to that GDB server. And then use wget to stage a couple of records in the database that will satisfy the left join. And then start building up your overflow data in the database, and then use wget to post the SOAP request. So how much overflow data do you need to build up in the database? Well, it's a pretty simple matter of just repeating that process until you get a crash in GDB. And then to trigger the exploit, this ridiculous wget incantation will actually post your SOAP request. When you do that, if you get a crash in GDB, hopefully you see something beautiful like this. Here we have highlighted in yellow program counter containing our data, and program counter is analogous to EIP on x86. In addition to that, you have all of these S registers also containing our data, and the S registers are just general purpose registers on Mips. So we control the program counter, which means that we can control execution and decide for ourselves what the program should do next. And we also control all of these S registers, and that's incredibly useful for developing our ROP exploit, which we're going to have to do in a little bit. But controlling the program counter isn't the same as actually getting execution. And I have to say, in developing this exploit, I had the program counter really easily. I mean, as you can see, this is This is a pretty trivial vulnerability. Actually getting execution to work reliably on the system was where I actually spent probably 85% of my time. So we have some challenges ahead of us. First is the fact that the stack is randomized, so we have to somehow find a way to defeat that. Also, there are some idiosyncrasies with the Mips architecture that you may not be familiar with. And you may be disappointed to know that ROP is somewhat limited on Mips compared to x86, if you're familiar with how ROP works there. We also have to deal with some bad characters, not just due to HTTP, but due to the fact that we're exploiting a SQL injection. There are some things working to our advantage, though. First, even though the stack is randomized, the heap and libraries aren't. So we'll be able to take advantage of that to find a lot of ROP gadgets in the libraries that we'll be able to make use of. The stack also is executable. So assuming we can locate the stack, we should be able to return into it and execute our shellcode. So how does ROP on Mips differ from x86? Well, one of the biggest problem is the fact that all Mips instructions are 4 bytes long, and Mips memory accesses have to be aligned on 4 bytes. And what this basically means for you is that there's no opportunity to return into the middle of an instruction and have that instruction be decoded as some other instruction. And this really reduces the number of ROP gadgets that you can potentially take advantage of. Fortunately, we can still find some pretty good ROP gadgets that do things like manipulate registers, load data that we control into program counter, and even help locate the stack and defeat ASLR. So how do you locate the stack using ROP? Here's my gratuitous IDAPRO screenshot showing an instruction sequence that loads several offsets from the stack pointer into registers S3, 4, and 6, and then subsequently jumps to whatever is in register S0. Now, remember that we control all of the S registers, so all we have to do is make sure that S0 contains the address of another ROP gadget that will in turn jump to whatever is in register S3, 4, or 6, and that gets us back into the stack. All right, Mips cache coherency is kind of an interesting problem that we have to deal with. Mips has 2 parallel caches on the CPU, one for instructions and one for data. Our payload was written to the stack as data, which means it is residing in the data cache and not in main memory until that cache is flushed. And so we can't execute our payload until it gets flushed out to main memory. So how do you flush the cache? Well, you could just do a really big write to the stack and fill up the cache and trigger a flush, but you might not be able to overflow a buffer with that much data. Fortunately, Linux provides a cache flush system call that you can use. And in fact, I believe if you check the man page for cache flush, it'll even tell you that the system call is only implemented on Mips. So there you go. If you can set up the parameters for cache flush properly and then ROP into it, then you can force the cache to be flushed and then start executing your code off the stack. We also have to deal with bad characters. So bad characters are not an original problem, right? So spaces break HTTP, null bytes break string handling functions, but we're also exploiting a SQL injection, and SQLite has its own set of characters that it'll specially interpret unless they're properly escaped. Fortunately, SQLite provides an escape sequence that we can use, so it's just a matter of escaping any of those bad characters when they're in your shellcode. And fortunately, that escape sequence doesn't conflict with any of the other bad characters for HTTP or anything else. So you just escape your SQLite bad characters like that, and that takes care of that problem. Now, the NOP instruction on Mips is kind of a pain, right? Because it's all null bytes. But it's not too hard to deal with. You just need to use some other instruction that's either inert or doesn't have any effects that you care about. And so that's how you deal with that problem. Now, this is where I actually spent most of my work, most of my time on this project. This was just kind of ridiculous. Metasploit provides you with one payload and one encoder for Mips. And I was never able to get it to work. If I attached to the process and single stepped through the decoding and execution of the payload in a debugger, it would work every time. If I didn't have a debugger attached to it, it would crash every time. And I never did sort out what the problem was there. And I'm really embarrassed to say how long I spent trying to sort through that. What I ended up doing was just bailing on Metasploit altogether, wrote my own payload that doesn't have any null bytes in it, and then therefore doesn't need a decoder. Now, kind of a tip, if Indianness sort of messes around with your head the way it does mine, and we're dealing with a little Indian architecture here, you can do things like set your callback IP address to all 10 so that byte order doesn't matter, and then do that until you get issues with your payload sorted out, and then figure out the Indianness later, or don't figure it out at all, as the case may be, like I did. Anyway, in a bit, when I show you the exploit, you'll actually see the exploit staging the overflow data in 3 pieces. So there's the initial overflow data, which is just sort of a random string that overflows the buffer. And there's a ROP chain, which overwrites the return address and sets up a sequence of ROP gadgets that will do things like flush the cache and help us locate the stack. And then the third piece is the actual TCP connect back payload, which will connect back to our system and give us a root shell. Okay, now it's time for a little demo. Now in the demo, I'm actually going to show you 2 exploits. One is the exploit that extracts sensitive files from the system, and then the second exploit exploits the buffer overflow, giving us a root prompt. Once we get the root prompt, then I'd also like to show you how you can start uploading some files to the system to transform it into kind of a useful attack platform. Now, bear with me for just a second while I switch screen modes. I want to be able to mirror the display so that I can see the same thing you're seeing. All right, so we go over here. Actually, I'm going to kill these terminal sessions. Try them again. Oh, I think I see what the problem is. Display. Let's let the demo god see what this. All right, confirm that. Sweet. All right. Let's go demo. It's going to work. There we go. Resize these terminal windows a bit. Okay. Right. So the first exploit, like I said, will allow us to actually extract some sensitive files from the file system. Now, in the slides, I actually showed you extracting etc password. Now, I have to confess that etc password only gets created on the system when you plug in a USB drive, because for some reason Samba creates it. But let's just punt on etc password, since that's not always going to be available. And maybe let's actually try grabbing the entire device configuration. So I've wrapped up the exploit in a little Python script. And I'm going to tell it to give us dev mtd block 14. And this block device actually points to is a way of accessing NVRAM. So if we can get that, we have all of NVRAM and the entire device's configuration. So what's going on? Try it again. Okay, so what we see here is the exploit actually making sure the old record isn't already there, then creates a new record that points to dev mtd block 0, and then gives us a URL that we can pull back our fake album art file. So if you run strings across what we've got, and grep for things like password, thanks. Okay, then we start seeing things like WPA passwords, admin passwords. There's all kinds of interesting configuration data in there. So we have the entirety of NVRAM, the entire device's configuration, in one really trivial exploit vulnerability. All right, the next one that I want to show you is where we exploit the buffer overflow, and we actually get a root shell. So I wrote a little program here that this is basically like Netcat listening for a connection, but I wrote it in Python to give us a little bit better output. So I'm going to use that. And then that's in the right window. And then in the left window, I'm actually going to run the exploit. And we'll see injecting the pieces of the payload, and once it has done that and triggered the exploit, then we'll actually see the connection come in the right-hand window. It's also giving us a running SQL injection count. And then we should see the connection come in here in the right-hand window. Boo. What has just happened? Well, that kind of sucks. All right, I'm going to reboot the router. I'm assuming we crashed the application. Oh, no, I know what the problem is. Okay, while I'm rebooting the router, so the only time this exploit ever fails is when I actually forget to set my callback IP address properly. So presumably the exploit worked, and I just didn't have the right IP address. So there we go. All right, we'll give it one more try. Wait for the router to come back up. So in a bit, and hope I'm not running out of time. I think I'm doing okay. Then in a bit, once we get the root prompt, then like I said, I'll actually show you how we can start loading some tools on the device and kind of transform it into an attack platform. I'm going to use my Albumart inject tool again because it won't crash the program, but it'll let me know. Okay, so the application is up and running. That's good. Okay, let's try one more time. Start up callback server. Okay, so it's clearing out the existing exploit data in case that happens to be there in the database. It's staging the exploit. My progress bar never looks right if the window's too small. Staging the exploit. And then in a bit, we should see the connection coming in. Okay, there we go. All right. Root prompt, right? I promised a root prompt, and then there we go. So it's like this talk almost happened. Okay, so sometimes on these little embedded devices, the only kind of service that you have running might be something like a Telnet session. In fact, I'm going to start up a Telnet server right here, just because our shell session is not a very good one. We don't have any command history or anything like that. So actually, let me start up Telnet and then exit out, and then Telnet into it, so we have a little bit more of a usable environment. Okay, so now we're Telnetted in. So sometimes the only service you have available to you is Telnet, and that you don't really have a way of getting files onto the system. So I wrote a little program called Telnet Ftp, which will actually transfer binary files over a Telnet session. That's pretty useful. So that's not what I wanted. Okay, so this program actually is actually kind of slow. So you don't really want to use it to transfer very large files. So what I'm doing is transferring a TFTP client. And then once we have the TFTP client on there, we can use it to pull down some larger files. And I think the TFTP client compressed that I'm uploading is like 22K, and it takes like a little over a minute to upload it. So once I get TFTP on there, then I can go over here to my Telnet session and uncompress TFTP and use it to pull some other files on there. And in a bit, I'll show you that I can put TCP dump on there, and I've gone ahead and cross-compiled TCP dump for Mips Little Endian. And then we can use TCP dump to start sniffing traffic that is coming through the router, which is potentially everyone's traffic, who is on the network. I'll wait just a little bit for this to finish off. And all it's doing is basically calling the echo command on the remote in and passing in, hex-escaped. A hex-escaped representation of the binary file, and it just drops it into /temp. And then at the same time, I also started up a little TFTP server. So let me actually go on to the go into the Telnet session and then use TFTP to transfer a file. Okay. And then we've got TCP dump on there. So now there you go. We're sniffing traffic coming across the device. Okay. I ask you to bear with me just a little bit longer while I switch displays, and I just want to finish off a couple slides. And then we should have, I think, plenty of time for some Q&A. All right. Okay. So what could have been done so this device would be a little bit less insecure? Well, I would submit that first and foremost, like it or not, this device isn't just a piece of consumer electronics gear. It isn't just a toy. It actually plays a critical security role on a user's network, right? It's a boundary device. It's a firewall. It should have security requirements established for it from the get-go, and those requirements should be designed for and developed for and tested. Okay, so for example, it should be capable of self-protection, which it clearly has failed at, right? It should also be capable of affording you some level of network protection, which clearly has failed at. I can get on the device and start attacking your network. I can actually turn the device against you. So this isn't just a toy that you use to serve up multimedia. It actually should be protecting you. It should be protecting your network. Also, I would submit that just better coding practices would go a long way. I mean, it isn't 1996 anymore. Why are we still using unbounded sprintfs and stir copies? Can someone please explain that to me? That's a rhetorical question. Please no one answer. But there are functions that help you do the bounds checking. And SQLite even provides you functions that, if you use them properly, will help protect you against SQL injection. And none of that is being used. And they're actually really easy to use. So just some better coding practices, I think, would go a long way. Some amount of privilege separation. We have the benefit of using Linux here, right? So Linux is capable of having multiple users and unprivileged users, and yet everything on this device is running as user ID 0. There's no reason for the Dlna server to be running as user ID 0. It isn't doing anything privileged. It doesn't even bind to any privileged ports. Okay, so just having maybe multiple users and separating things out that way would also help. Now, a lot of people's experience with SE Linux may be the thing that you turn off when you install Fedora on your laptop because you don't want it to break your stuff, right? I used to work for a company called Traces, and at Traces we had a lot of experiences developing hardened appliances using SE Linux. And I can tell you that appliance-type devices are actually an area where SE Linux does really well, because there are very few applications on the system that you need to confine, and you have very little direct user interaction, and you don't have users adding and removing applications and creating data like that. So SE Linux actually potentially could do really well on this system. And in fact, if the system was compiled with SE Linux and had an enforcing policy, it would completely mitigate both of the exploits. The application wouldn't be allowed to access sensitive files. The application also wouldn't be allowed to execute programs. So if you did successfully exploit a buffer overflow, you would have a very limited environment to work with. You wouldn't be able to execute binsh, for example. So it should theoretically be possible at least to develop a single SE Linux policy and apply it across the board to all the devices and just add and remove policy modules as you need to confine different features. All right, so what's the upshot here? Well, the developer here in this case has assumed well-formed data, right? Because only his application ever puts data in the database. So how could anything in the database be bad? Well, we're able to compromise the database and violate those assumptions. And we're able to do that even though nothing in the database itself is particularly valuable. All right. Here's my contact information. If anyone after Black Hat, after the talk, wants to get in touch with me and has any questions, feel free to get in touch with me that way. But while we're here today, I'm also happy to take any questions right now that you may have. Yes.
Most commonly the WP is on this router from this maker. Do you go out there and try to fetch additional firmware from other vendors that may use the same base board, the same board, the same base design to see if they will also be affected by the vulnerability?
So I believe the question is, once we've analyzed this firmware and found these vulnerabilities, then do we go and look at other firmwares from other vendors that may be using the same system on a chip, and the firmware could be based on the same SDK and software stack? That is actually something at TNS that we do quite a bit of, and I can tell you there are a number of vendors, and Netgear so far isn't among them, but there are a number of vendors where when we're analyzing the firmware, we actually find strings from multiple vendors in the firmware. So this sort of thing happens all the time, where you find some vulnerabilities and those same vulnerabilities are present in other firmwares. Yep.
If you disable Dlna, you're safe with some of the exploits you talked about. And can you actually disable that? Because I've encountered so many routers where you just can't disable it.
No, that's a very good question. So the question is, if you turn off DLNA on this router, are you protected from these specific exploits? And is it even possible to turn off DLNA on this router? Yes, it is. That's a configuration option. You can turn off DLNA. Oftentimes in the case, like you pointed out, there are features that you try to turn off and either it just doesn't respect your wishes or there's no option to turn it off. So yeah, you can turn off DLNA in this router. And if you do, these specific exploits won't work. I will tell you that we've got a bag of tricks on this router that I'm not going to share with you today that have nothing to do with DLNA. So there's some other things that you can't protect yourself against. That's a good question. So the question is DLNA listening on the public interface? No, it is not. And so the specific exploits that I showed you today in their current state only work on the LAN interface. I have a couple things to say about that. One is, if you're familiar with Reaver and WPS, which TNS also released, this device is vulnerable to Reaver. So as long as you're on the premises, you can extract the WPA key that way and get on the LAN. Also, Craig briefed a tool at Black Hat a couple of years ago called Rebind. And Rebind is able to proxy HTTP requests through a victim's web browser using JavaScript to the LAN side of the router. Now, I haven't yet gotten these exploits to work with Craig's Rebind tool, mainly because the JavaScript mangles my SQL injection, but it is at least in theory possible to make that happen from the internet using Rebind. So I think there was a question from this direction. Okay. All right. Yes?
Why didn't you use Telnet enabling that's already on there?
No, that's a good question. Yeah, so the device actually has its own little backdoor password. It's got Telnet already running, and so why did I go to the trouble of writing up a paper and submitting it to Black Hat talking about buffer overflows and SQL injection when we can just use Telnet enable to turn on Telnet? Well, so there are actually a lot of easier ways on this device, not just through Telnet. The reason I did it this way is because I thought it was actually a pretty interesting talk. There's not a lot out there on Mips Overflow, so I kind of wanted to be able to talk about that. And it was kind of fun to sort of combine the SQL injection and exploit a buffer overflow. So mainly because I thought the exploits were a lot of fun. Yeah. Yes, over here. No, I did not submit these vulnerabilities to Netgear. And I suspected someone might ask that question, so I was prepared ahead of time with our company's official policy, and Tactical Network Solutions' official policy is not to report vulnerabilities to vendors. Any other questions?
Have you looked at ways to actually replace the entire firmware on the device so that it performs the function it's supposed to, but then in the background gives you all the functionality? Okay. I think your question is, have I looked at a way to replace the firmware so that it continues behaving the same way it always does, but I've maybe Trojaned the firmware?
Yeah, that actually is a personal project that I have going on, not with this router, but with some other routers. But I mean, it's very easy to modify the firmware and then repack it, and as long as it passes whatever checksum, the device is looking for. Like it's not cryptographically signed or anything like that. So yes, so you could theoretically Trojan the firmware and do that. Mm-hmm. Any other questions? Well, awesome. I tell you what, I really appreciate everybody, coming out to hear my talk and taking the time to listen to me babble. I hope this was pretty interesting to everyone. So thanks a lot for coming.